Hello, everyone. This is our ECE 4960 protection system design project for the fall of 2025. Um, this project was sponsored by CAPER, which is the Center for Advanced Power Engineering Research. Um, it is by Corey Adkins, Joe Horn, Max Swafford, and Adam Wachter. Our advisors for this project were Dr. Drew Clark from Duke, Dr. Rampton Hadidi from Clemson University, and Dr. Hassan Raza from Clemson University. So, a little bit of a project overview. So, this project is kind of split into two 1 semester long projects, but we're just doing the 1 semester long project. So for the deliverables, it was to develop a set of protection requirements and settings for a provided distribution feeder, while also keeping in mind reliability, resiliency, and asset service life. So this all includes transmission to distribution transformer, the distribution bus, the distribution overhead feeder with and without energy resources with reclosers and fuses, and also the distribution underground feeder without DER with downline medium voltage switchgear protection. This also includes that we had to build a physical model of our protection schemes to simulate all the above mentioned protection schemes. So here is the provided topology information circuit that was given from Duke. So here you can see starting from the left that we have it's energized by a 115 kV primary. It is then stepped down through two transformers to 23 kV secondary, where it is then distributed to the rest of the circuit model. Um, we are also given three primary breakers, which include the 370, 371, and 373 breakers, and they each include downline, each include protection devices such as relays, reclosers, and fuses. And based on these devices, we were also given, aspects such as CT ratios, and we had to uh, find out time curves and various pickup information. We were also provided with the fault information for each device across all circuits, and the type of fault information that were included were both three-phase, line to ground, and line to line fault magnitude values. Motivation. So all team members in this project have an interest in pursuing careers in the power industry. All of us are EEs. With that being said, we also wanted to gain real world experience in both power related skills and system protection. We also wanted to work and communicate with industry personnel and advisors, which were listed in the beginning slide. And we also wanted to demonstrate and apply our electrical and power engineering knowledge in a practical manner that would that can then relate to everyday power devices and systems.
So for our problem definition, we have that the bulk electric system, or the BES, is constantly changing from transmission lines reconductoring to accommodate increasing load demand, to adding new distribution feeders for new developments, as well as adding protection devices for improved reliability and more. So the electric grid is always constantly changing and modernizing, but it's going at a very slow rate for multiple reasons and challenges that we face, such as the cost, safety, reliability, and complexity of the circuits and outdated infrastructure. So, for example, uh, the reason it's going so slow, if we were to try to replace some of this or upgrade, and something were to happen, like a power outage, or we have our systems that are not properly coordinated, that can cause a power outage for millions of people within a matter of minutes. And it's a very difficult process to upgrade because it has a lot of safety standards. So the goal of this project was to develop a set of protection requirements and settings, as well as develop a hardware test bed for a given distribution feeder, while keeping in mind reliability, resilience, and asset service life, to sort of demonstrate these changes. So for our block diagram, from our how our circuit works, power is fed in from the transmission bus. the fault detection goes off whenever a fault occurs. It then isolates our fault. Once the fault is isolated, our PLC then reads in the input from the fault, sends a logic, runs through a logic gate, and then sends an output back out to the circuit breaker. It says basically trip the circuit breaker here where the fault is located. The circuit breaker trips, and then the breaker on the HMI then opens up and stops the fault. So for description of our design, so we have our physical model hardware. Uh, Basically, it's a scaled down version of the given circuit that we showed. It's unpowered model that consists of a transmission bus fed into a transformer that then connects to a bus that branches out to our breaker that is connected to a fuse and a recloser to basically show from start to finish how the process would flow. The test bed contains an HMI and LEDs to visualize the fault zone and show which device tripped due to the fault. A combination of physical model and digital output allows a user with no experience in protection to easily understand where the fault occurred and which devices are activated or affected. I'm sorry. For our power world or our software model, circuit modeled after the given distribution feeder using buses to represent each device, such as breakers, fuses, reclosers, relays, etc. For the design, given data such as impedance, nominal voltage, device type, and calculated values such as pickup settings and load calculations were integrated and tested for accuracy. The simulation model is used for calculating our fault currents to then be used by our PLC. And now for the software about Python, PLC, and our HMI, Python script reads in fault currents and locations from our power world that is saved into an Excel file. Python then writes the location to PLC and displays the location on our HMI screen to represent our physical model. And specific cases are hardwired into our physical model for efficiency. So we only have like a specific line while Power World has the entire circuit.
And now I'll go over our performance analysis. So for the pickup settings, which include the fault current and pickup times, they're calculated and then imputed into PowerWorld, which match closely with the given Caper fault magnitude data that we have in the Excel files. And then our TCC or time current characteristic curves follow coordination logic, which ensure that upstream breakers and devices coordinate with the downstream devices. And we have a physical teaching model that also helps to show industry experience and protection principles. So some strengths of our project are a user-friendly layout that is easy to navigate and recreate. This can also be scaled to incorporate additional data and overall feeders. The addition of the hardware teaching tool to the project helps bridge the gap between theory and practice, which allows those who have no technical experience in the power industry to better understand the steps of power system protection. And lastly, it provides real world utility experience. And now some weaknesses. This project requires a decent amount of technical knowledge and power system protection to fully understand the technical side of the project. Some of that knowledge might include like CT ratios, load and fault current, TCC curves, coordination logic, etc. PLC ladder logic and integration with PowerWorld software can and has been tricky and time consuming. Project accuracy is dependent on calculated data, which is then needed to input in PowerWorld, which is then sent to the PLC to execute.
So for our senior design project, we worked on a power protection system teaching tool. The idea is that we have these basic distribution system with protective devices that can catch a fault on the line if one were to occur. For each individual device. We've got 3 breakers, a recloser, and a fuse. To accompany this, we also have a bit of a control box, so to speak, to show the circuit de-energizing. I've got an HMI screen here that can better visualize what that looks like. So, if let's say a fault were to occur here at the second breaker, or manually you can come over, activate it. This green light indicates that the circuit is de-energized here. And if you look at our HMI model, you can see that a fault's occurring here, and it kills the power for the rest of the line to protect the rest of the circuit. Now, we have a CM5 Automation Direct HMI. We have a Productivity 2000 PLC, complete with power supply, CPU, and 2 input and output modules.
We're also using 24-volt power supply to power the PLC.
Yes. So, a little bit behind the ladder logic of the system. The idea is that you've got inputs, but real interestingly, you also have these specific lines that mention Python. Well, a cool feature of our project is that to accompany it, we have a simulation made in PowerWorld by one of our teammates, Max Wofford. And the system will go as far as to a system. You could select a fault from here, and it will show up on the HMI function. So, no faults, nothing going on. Let's say we want a fault. So you come to fault. Single fault lines. Make sure when you run calculations, you got your 3-phase balance fault type. You got amps. Now you can calculate the fault currents in your system. With this information, you can come over, take all of it, and pull open this Excel file. At its simple name, fault.xlsx. You can come over, paste in all of that information, save it. Now, come over to our Python file. You just run the command Python data five. You'll see that we have a fault location, at least internally for the PLC, at location 2. Now, for our model, this triggers fault 2 in our system, which on the screen looks like this.